Imagine closing your eyes and sinking slowly into a vast body of water. The surface above grows dimmer with every breath you take, until it disappears completely. Around you there is nothing but shades of blue that fade into black, a silence broken only by your own heartbeat. This is the ocean, deep, ancient, and largely unknown. Strangely enough, we know more about the surface of the moon than about the seafloor beneath our own planet. That fact alone sets the tone for what you are about to explore. Tonight you are not traveling upward into the stars. Instead, you are drifting downward into a world that has existed far longer than humans, far longer even than forests or flowers. The ocean is where life began, and it still hides its oldest secrets. More than 70% of Earth's surface is covered by water. That is a simple number, but it is worth pausing over. Nearly 3/4 of our planet is ocean, yet most of it remains unseen. We can map galaxies millions of light years away, but we still have not mapped the deepest trenches of our own seas in detail. The Mariana Trench, for example, plunges nearly 7 miles into the Earth. If you dropped Mount Everest into it, the peak would still be more than a mile underwater. What lies in such darkness? Scientists estimate that up to 2 million species may still be undiscovered in the ocean, perhaps many more. And yet this watery world is not just unexplored space, it is our oldest home. Billions of years ago, Earth looked nothing like it does now. Continents as we know them had not formed. Volcanoes belched gases into the sky. Meteorites struck with regular force. The surface was a hostile place, and yet in the oceans, something extraordinary was happening. Tiny cells, fragile but determined, were learning how to divide, how to use sunlight, how to exchange energy. They were the earliest forms of life. Without the shelter of the seas, it is doubtful they could have survived. Water buffered them against the violence of the young planet. It absorbed radiation, it stored heat, it carried nutrients. If you think of Earth as a living story, then the first chapters were written in liquid ink. Even today, when you walk along a beach or hear waves crashing against cliffs, you are listening to echoes of that beginning. The salty taste of seawater is not random. It mirrors the chemistry of the fluids inside our own bodies. In a way, each of us carries a little ocean within us. Blood plasma shares similarities with seawater because our distant ancestors evolved inside it. To understand the story of life, we cannot start on land. We must return to the water, to the cradle that nurtured every lineage, every experiment, every new form. But there is a second reason why the ocean matters. It is not only a memory of the past, it is also the engine of the present. The ocean regulates climate, drives weather, stores carbon, and provides half the oxygen we breathe. Microscopic organisms floating in sunlit shallows pump out oxygen with every moment of their existence. The fact that you are able to lie back now, breathe calmly, and listen is thanks in part to the quiet work of ocean plankton. Without them, the atmosphere would be unrecognizable. Life on land, including our own, depends on this hidden web. If the ocean seems mysterious, that is because it is. The average depth is more than 2 miles, and beyond a few hundred feet sunlight vanishes. In that eternal twilight, strange forms drift, translucent creatures, glowing predators, organisms that look more like dreams than like animals. We call this the deep sea, but really it is a planet within a planet. Entire ecosystems thrive there without light, depending instead on chemical energy seeping from vents in the seafloor. Tube worms grow taller than a person, feeding not on plants or prey, but on symbiotic bacteria. Crabs gather near black smokers, vents that release mineral-rich water so hot it could melt metal, and somehow they survive. These places remind us that the ocean still carries possibilities we hardly understand. It is worth pausing to recognize just how small our perspective is. Human history is only a few thousand years old. Civilization, as we normally define it, stretches back maybe 12,000. By contrast, the ocean has been shaping life for over 3 billion years. That is 3,000 million years. Imagine counting seconds. After 12,000 seconds, only a few hours have passed. After 3 billion seconds, nearly a century has gone by. Now translate that difference into years, into lifetimes, into entire worlds rising and vanishing. That is the scale of the ocean's story. For most of that time, land was barren. No trees, no flowers, not even grass. The continents were silent stone. If you had walked across them, you might have found only lichens clinging to rock. But the seas, those were alive. Every ripple of current carried organisms too small to see, or creatures larger than your hand, but stranger than any modern animal. The ocean was the first canvas, and evolution painted with endless shapes and colors. Some were fleeting sketches, erased by extinction. Others were masterpieces that endured, ancestors of creatures we still know today. Think for a moment about what it means to say prehistoric ocean. Prehistoric usually brings to mind dinosaurs, mammoths, or cave paintings. But the oceans were ancient long before any of that existed. When dinosaurs rose to dominance on land, the seas had already hosted their own empires for hundreds of millions of years. Reefs had been built and destroyed, predators had risen and vanished. Entire ecosystems had cycled through glory and collapse. The oceans had their own dynasties, as grand as anything on land. Though their rulers were often creatures that today would look alien, this is where your imagination becomes a kind of time machine. As you listen, you are invited to let go of the present moment. Picture yourself floating in warm, shallow seas, long before humanity existed. The water is clear, sunlight breaks into golden shafts, and beneath you lies a world you have never seen. Creatures crawl across the sand with jointed legs, others drift like ribbons. Some carry shells, and others swim with jagged teeth. You are not in a fantasy, you are in Earth's own history. By listening, you are stepping backward into the ocean's memory. In this chapter, you can allow yourself to rest, to breathe slowly, and to simply follow along as the story unfolds. The ocean invites you to let go of urgency. Unlike human time, which rushes from one moment to the next, ocean time is slow, patient, almost geological. Waves rise and fall, currents move with the turning of the planet, and life adapts over spans so vast they are almost beyond comprehension. Tonight, your task is not to memorize names or numbers, but to drift, to picture, to feel, and to let the weight of deep time settle around you like water. Before we move further back, it helps to know why the ocean is so good at preserving and erasing history at the same time. Water is both a cradle and a destroyer. Bones dissolve quickly in salt water, wood and leaves rot away, even shells are ground into sand by waves. And yet, under the right conditions, the ocean can also capture a perfect record. A sudden burial in fine sediment can seal away a creature for 500 million years. That is why fossil beds like the Burgess Shale or Chenjiang exist. They are windows into entire lost worlds. Most of those worlds are gone without a trace, but a few survive just long enough for us to find. This balance between memory and forgetting defines the ocean's story. It explains why we can study trilobites in exquisite detail, yet never know the full variety of life that once swam beside them. It explains why we can reconstruct mass extinctions, but also why so many questions remain. The ocean is not generous with its secrets, but it gives just enough to keep us searching. And that is what this journey is, a search, not for treasure or lost ships, but for understanding. We are going to move back through time, slipping deeper into eras, when the oceans were the stage for experiments unlike anything we know today. We will see the first predators, the builders of reefs, the armored fish of the Devonian, the reptilian giants of the Mesozoic, the colossal Megalodon, and finally, the strange survivors that still swim among us. Each step will reveal a different ocean, with its own rulers, dramas, and mysteries. The first stop takes us back over 500 million years, to a time when the seas erupted, with life in forms so unusual they seem almost alien. It is called the Cambrian Explosion, and it marks the true beginning of Earth's great marine story. You sink further into the ocean of time, carried gently backwards by imagination. The world above is young, the continents bare and quiet, but beneath the waves, something extraordinary is about to unfold. This is the Cambrian period, over 500 million years ago, and it marks one of the most dramatic turning points in the history of life. In the blink of geological time, the oceans will transform from simple landscapes of microbes into bustling kingdoms of creatures. Scientists call it the Cambrian Explosion, and it was exactly that, a sudden, spectacular bloom of complexity. For billions of years before this moment, life had been modest. Single-celled organisms dominated, drifting in currents or clinging to sediments. From time to time, larger forms appeared, like the soft-bodied creatures of the Ediacaran seas, delicate fronds, quilted forms pressed into sand, but compared to the diversity we know today, it was a quiet world. Then, around 541 million years ago, the pace of change quickened. In only 20 or 30 million years, the oceans filled with new body types, new behaviors, new ways of surviving. It was as though nature had turned a page and begun an entirely new chapter. Imagine looking across a Cambrian seafloor. At first glance, it might appear barren, but as your eyes adjust, the strangeness comes alive. Jointed creatures scuttle along the sand. Long, ribbon-like predators glide in the water above. Soft-bodied worms push through sediment, while spiny, armored forms crawl awkwardly across the bottom. Nothing here looks quite familiar. These are experiments in evolution, the first drafts of designs that will echo across the rest of life's history. One of the most successful of these designs belonged to the trilobites. They are perhaps the most recognizable Cambrian animals, with hard, segmented exoskeletons, many-legged bodies, and compound eyes that glittered like tiny mosaics. Trilobites came in astonishing variety, some shaped like small coins, others stretching over half a meter long, their shells preserved beautifully, leaving behind fossils by the million. They were not only abundant, they were adaptable. Some grazed peacefully on the seafloor, others burrowed, rolled up like tiny armored balls, or swam through shallow waters. The trilobites would survive for hundreds of millions of years, but here, in the Cambrian, they were pioneers, testing out the possibilities of being an arthropod. Sharing the ocean with them were predators of a new scale. Among them was Anomalocaris. Its very name means abnormal shrimp, though it was no shrimp at all. Picture a creature nearly a meter long, with large compound eyes scanning the water. From its head extended two jointed appendages, tipped with spikes for grabbing prey. Its mouth was a circular disc lined with plates, able to crush the shells of trilobites and other armored creatures. It swam by undulating flaps along its body, gliding like a ribbon through the sea. For a long time, scientists misunderstood Anomalocaris, mistaking its body parts for separate animals. A mouth thought to be a jellyfish, appendages thought to be shrimp. Only later did the puzzle come together to reveal one of the earliest apex predators. In a world where most creatures were small, Anomalocaris was a giant, and its reign marked the start of active hunting in Earth's history. Yet not every Cambrian animal was fierce. Some were simply strange. Take Hallucigenia, a creature no longer than your finger. Its body was thin, its back covered in sharp spines, while soft legs dangled below. When fossils were first discovered, paleontologists reconstructed it upside down, imagining it walked on its spines while waving tentacles in the water. Decades later, closer study showed the truth. The spines were armor, and the soft legs carried tiny claws that let it crawl along the seabed. Even its head was once drawn backwards. Hallucigenia lives up to its name, a creature so dreamlike it seemed more like a hallucination than a real animal. But it was real, and it thrived in Cambrian seas, another experiment in survival. Then there was Opabinia, one of the most peculiar animals ever discovered. It had 5 eyes perched on stalks across its head, and from its face extended a long, flexible proboscis ending in a claw. With this, it plucked food from the seafloor and passed it back to its mouth. To our eyes, Opabinia looks like something out of surreal art, yet in the Cambrian, it was simply another way to live. The diversity of body plans in this era shows how wide open evolution was. Nature was trying everything: spikes, claws, armor, tentacles, even 5 eyes at once. Why did this explosion of forms happen? Scientists debate the causes. Some suggest oxygen levels in the atmosphere rose, allowing animals to grow larger and more. Others point to new ecological interactions. The evolution of eyes, for example, may have triggered an arms race. Once creatures could see, they could chase. Once they could chase, prey needed protection. Shells, armor, and spines became widespread. The predator-prey dynamic that still defines ecosystems today may have begun here, in these shallow Cambrian seas. For the first time, life was not just surviving but competing, innovating, and adapting in response to threat. The evidence for this period comes from rare fossil sites preserved under remarkable conditions. Among the most famous is the Burgess Shale in Canada. Discovered in 1909 by Charles Walcott, it contains fossils so detailed that even soft tissues are visible: gills, tentacles, delicate limbs, sometimes even traces of organs. Creatures we might never have imagined were revealed in stone. Another site, in Zhenjiang, China, offers an equally rich window into Cambrian diversity. Together, they show us that the Cambrian explosion was not a local event. Across the world, oceans filled with these extraordinary forms. Imagine standing at one of those sites today, holding a slab of shale in your hands. You split the rock carefully, and there, pressed in dark outline, is a creature that lived more than 500 million years ago. Its body is fragile, yet preserved as though it died only yesterday. In that moment, the distance of time collapses. You are face to face with a world long vanished. That is the gift of the Cambrian fossils. They let us see not only bones and shells, but the creativity of life itself. As you drift deeper into the Cambrian seas in your imagination, picture the play of sunlight through shallow water. Trilobites crawl in every direction, tiny eyes glinting. Above, an Anomalocaris glides silently, its grasping arms ready to strike. Hallucigenia creeps across the sand, spines raised like a miniature fortress. Opamina searches with its trunk-like proboscis, its 5 eyes scanning calmly. Each of these animals is utterly alien, yet each carries the same urgency: to find food, to survive, to endure another day in this new, crowded ocean. This was the first great bloom of animal life, and it set patterns that still shape us today. The Cambrian explosion did not only fill the seas with creatures, it created the very foundations of modern ecosystems. The body plans invented here, exoskeletons, jointed legs, jaws, eyes, were so successful that they continue in evolved forms in countless species alive now. The crab on a dinner plate, the insect on a window, the fish in a river, even the human listening to this story, all carry echoes of Cambrian ancestry. The Cambrian also reminds us that evolution is not always slow and steady. Sometimes conditions shift, and life leaps forward in bursts of creativity. The arms race of predator and prey drove new inventions. The rise of mobility and vision opened new possibilities, and once those pathways appeared, they spread, branching outward into endless forms. Life is not a ladder climbing upward, it is a tree, and in the Cambrian many of its first great branches spread wide. The oceans, once quiet, were now alive with motion. For the first time, animals swam, crawled, hunted, and defended with purpose. The story of survival had begun to write itself in shells and spines, in teeth and eyes. From now on, the seas would never return to simplicity. They had become arenas of competition and wonder, and yet, even this bloom was only the beginning. In the chapters that follow, the oceans will build vast coral kingdoms. Early fish will rise, and predators will reach new scales of power. The Cambrian opened the curtain, revealing the possibilities of animal life. What came next would shape the oceans into realms of beauty and danger beyond imagination. The Cambrian had been a burst of invention, a sudden experiment in forms and survival. But as time moved forward into the Ordovician and Silurian periods, the oceans began to settle into something richer, more stable, more recognizable as ecosystems. If the Cambrian was a sketchbook of wild ideas, the Ordovician was the moment those ideas became landscapes. Intricate communities layered with balance and purpose. Close your eyes and imagine shallow seas flooding over ancient continents. Warm waters spread across much of the Earth, creating broad continental shelves where sunlight could reach the bottom. Here, life seized the opportunity. Reef systems began to rise, not the coral reefs we know today, but the earliest true reef builders. These were formed by sponges, algae, and organisms called bryozoans, tiny colonial creatures that built delicate lattices of calcium carbonate. Together they created underwater frameworks, sheltering countless smaller animals. Reefs turned the flat seafloor into a three-dimensional city, where every crevice and corner became a home for life. Swimming through these Ordovician seas, you would see trilobites still thriving, their armored bodies glinting as they moved across the sediment. But now they shared the world with new actors. Brachiopods, creatures with hard shells but unlike clams, anchored themselves to the substrate, opening and closing to filter food from the water. Crinoids, also called sea lilies, grew on long stalks, unfurling feathery arms to catch drifting particles, like undersea flowers swaying with the current. Gastropods, ancestors of modern snails, grazed across surfaces. The seafloor was alive not just with individuals, but with whole communities interacting. It was in this age that fish, real vertebrates, began their slow rise. At first they were small and jawless, members of a group known as agnathans. They had long, eel-like bodies and simple mouths for sucking in food. Some wore bony plates for armor, turning their heads into living shields. They were primitive, but they marked the beginning of a revolution. For the first time, backbones entered the story. These jawless fishes were the earliest vertebrates, ancestors of the vast diversity of fish, amphibians, reptiles, birds, and mammals that would follow. To us, they may seem unremarkable, but in their time they were pioneers, the first to try out the architecture of bone and cartilage. Above them, the true giants of the Ordovician seas drifted and hunted. Cephalopods. Picture a creature like a squid, but housed within a long, straight shell that could reach several meters in length. These orthoconic nautiloids floated through the water, propelled by jets of water like modern squid, but much larger, their shells glistening with chambered precision. At their narrow end, tentacles reached outward, grasping prey. They were the apex predators of their age, dominating the oceans much as sharks do today. To encounter one would have been awe-inspiring, an armored spear moving with unexpected grace, commanding the open water. The Ordovician seas were dazzling in their abundance. Fossil evidence suggests that marine biodiversity may have increased fourfold during this period. Entire families of animals appeared. New mollusks, new arthropods, new echinoderms. Reefs became hubs of activity, with life teeming in layers, from the sediment dwellers to the free swimmers above. The Cambrian had shown what was possible. The Ordovician proved that those possibilities could knit together into stable ecosystems, thriving across vast areas of ocean. But the Earth is never static. Beneath the calm rhythm of waves, tectonic plates shifted, continents drifted, climates changed. Around 445 million years ago, the oceans faced one of their first great crises, a global cooling event triggered by shifts in carbon dioxide and glaciation plunged the planet into ice ages. Sea levels dropped dramatically as glaciers expanded, draining shallow seas where reefs and communities had flourished. For ocean life, this was catastrophic. Nearly 85% of marine species vanished in what we now call the Ordovician mass extinction, the first of the big five great die-offs in Earth's history. Imagine those thriving reefs suddenly exposed by receding waters, corals and sponges bleaching in the sunlight. Imagine whole shoals of trilobites swept away by changing currents, cephalopods stranded as ecosystems collapsed. It was a stark reminder that life, no matter how creative or abundant, is always vulnerable to the forces of climate and geology. And yet, even in such devastation, survivors carried the story forward. From this extinction, the Silurian period emerged. As glaciers receded and seas rose again, ecosystems recovered. Reefs reappeared, stronger and larger. This time, corals began to play a leading role. Tabulate corals, with honeycomb-like skeletons, joined forces with stromatoporoids, sponge-like reef builders, to construct solid reef structures. These Silurian reefs were the ancestors of the great coral systems we know today, places like the Great Barrier Reef tracing their lineage back to these ancient beginnings. The Silurian oceans were calmer, warmer, and more stable. Life rebounded quickly, diversifying once again. Jawless fishes continued to spread, their bony armor thickening, turning them into slow but well-defended creatures. In some groups, paired fins began to appear, early hints of the anatomy that would one day give rise to limbs. Tiny cartilaginous fishes also swam in these seas, ancestors of sharks and rays. The blueprint for vertebrate diversity was expanding. Crinoids flourished, creating vast undersea meadows of waving stalks. Eurypterids, sometimes called sea scorpions, prowled through the shallows, some growing to several meters in length. These formidable predators foreshadowed the power struggles to come in later oceans. Trilobites adapted as well, evolving spines, different feeding strategies, and varied lifestyles to survive the shifting environment. But perhaps most impressive were the cephalopods, who remained lords of the open water. Some began to coil their shells into elegant spirals, the first true nautiloids resembling the chambered nautilus of today. Their mastery of buoyancy allowed them to rise and sink at will, giving them control over depth and hunting ground. In the clear Silurian waters, they must have been a breathtaking sight. Long-shelled or coiled creatures gliding effortlessly, tentacles splayed, eyes watching, apex predators that no other animal could challenge. The Silurian also marked subtle but important steps toward life on land. Simple plants like mosses and liverworts began to colonize damp shorelines, stabilizing soils and introducing oxygen into terrestrial habitats. Tiny arthropods may have crawled among them. Though the focus of this story remains in the ocean, it is important to note that the Silurian seas and the edges of their shores were preparing the stage for a revolution, the conquest of land. Through both periods, one lesson stands clear. Ecosystems were beginning to weave themselves into intricate webs. No longer were oceans dominated by isolated experiments. Now predators, prey, builders, and grazers formed balanced communities. Reefs became nurseries for life. Cephalopods ruled the open seas. Jawless fishes began the long journey that would eventually lead to vertebrates exploring every environment on Earth. If the Cambrian Explosion was the spark, the Ordovician and Silurian were the steady flame, spreading across the planet, illuminating the seas with richness. Even their crises, the first great extinction, became part of the pattern, pruning the tree of life, shaping survivors into new forms. The ocean was learning to host not just life, but complexity, resilience, and recovery. From here, the stage was set for even grander dramas. The next act would be the Devonian, remembered as the Age of Fishes, when armored giants and terrifying predators would seize the seas. But for now, in the Silurian waters, reefs are rebuilt, fishes are multiplying, and cephalopods still glide as kings of the deep. The ocean, tested by crisis, is stronger than before, ready to write its next chapter. The Silurian seas had been places of recovery, where reefs rebuilt themselves and vertebrates began to explore their potential. But as time moved forward into the Devonian period, something remarkable happened. Life in the oceans leapt ahead once again, and this time the focus was clear: fish. The Devonian would come to be known as the Age of Fishes, and with good reason. Never before had vertebrates taken such a commanding role in the seas, filling niches from the shallow reefs to the open waters, experimenting with armor, jaws, fins, and even the first tentative steps toward land. Picture the Devonian Ocean. Sunlight filters through warm, shallow seas that stretch across continents. Reefs of coral and stromatoporoid sponges grow vast and intricate, rivaling modern systems in size. Within these underwater cities, countless species find shelter: brachiopods, trilobites, crinoids, and mollusks. But the real spectacle comes from the fish. Where earlier seas had seen primitive, jawless forms, now the oceans swim with jawed vertebrates of astonishing variety. Some are small, quick, and agile. Others are monstrous, armored like tanks. Among the most extraordinary of these was Dunkleosteus. Imagine a predator nearly 10 meters long, its head encased in bony plates, its jaws not lined with teeth, but with sharp interlocking edges of bone. With one of the most powerful bites of any animal in history, Dunkleosteus could crush through armor and bone alike. Studies suggest its bite force may have rivaled that of a modern crocodile many times over, easily snapping the shells of other fish or even other armored predators. It was a top hunter, roaming the seas with a body both fearsome and efficient. Yet despite its terrifying appearance, Dunkleosteus was a pioneer, one of the earliest truly massive vertebrate predators in Earth's story. But it was not alone. Across the Devonian seas swam a diverse cast of armored fishes, known as placoderms. These creatures, covered in bony plates around their heads and thoraxes, displayed a wide range of forms. Some were small bottom dwellers, scraping the seafloor for food. Others, like Dunkleosteus, were giants patrolling the open water. Placoderms were evolutionary experiments in how to build a predator, how to balance protection with agility, how to use jaws for new kinds of feeding. For hundreds of millions of years, no vertebrates had jaws at all. The Devonian changed that. With jaws came new possibilities, the ability to bite, to grip, to chew. The invention of jaws was one of evolution's great turning points, and in the Devonian, it reshaped ecosystems forever. Alongside placoderms, another group was quietly establishing itself: the sharks. Early sharks were not quite the sleek hunters we imagine today, but their lineage was already visible. They had cartilaginous skeletons, lighter than bone, giving them speed and flexibility. Their bodies were streamlined for swimming. Rows of teeth lined their mouths, easily replaced as they wore down. Though smaller than the armored placoderms, sharks were fast, opportunistic, and endlessly adaptable. In time, their design would outlast the heavy armor of the placoderms. What the Devonian shows us is the beginning of a rivalry: heavy, plated hunters versus agile, toothy swimmers. But the story of the Devonian seas was not only about predators. In quiet backwaters and shallows, another kind of fish was preparing for a revolution. These were the lobe-finned fishes, or sarcopterygians. Unlike the thin ray-like fins of most fishes, lobe fins had thick, fleshy bases supported by bones. Within those fins were structures that faintly resembled the bones of arms and legs. At first, these fins simply helped the fish maneuver in tangled, shallow waters, pushing themselves through vegetation or across muddy bottoms. But over time, those bones would lengthen and strengthen, laying the foundation for the first limbs. These were the ancestors of amphibians, reptiles, mammals, and humans. The Devonian oceans, in their quiet corners, were beginning to whisper the possibility of life on land. One of the most famous of these lobe-finned fishes was Tiktaalik, discovered in Arctic Canada. Tiktaalik lived around 375 million years ago, near the end of the Devonian. Its body was a mosaic of traits. It had gills and fins like a fish, but also lungs and rib structures that could support it in shallow water. Most strikingly, its fins contained bones resembling a shoulder, elbow, and wrist. Tiktaalik could push itself up, lifting its head above water, peering out into the unknown world beyond. It was not yet a land animal, but it was a bridge between worlds, showing how fins could become limbs. In other corners of the Devonian seas, ray-finned fishes, ancestors of the vast majority of fish today, were also taking shape. Unlike lobe fins, their fins were light and fan-like, supported by thin rays of bone. These fins gave them speed and precision. Over time, ray fins would diversify into nearly every aquatic niche, from tiny minnows to massive oceanic hunters. The Devonian was their dawn, a time when both branches of fish, lobes and rays, began their separate journeys. One would conquer the land, the other would dominate the waters. All of this took place against the backdrop of reefs that stretched for miles. Devonian reefs were some of the largest in Earth's history, vast limestone structures built by corals and sponges teeming with life. They hosted brachiopods, gastropods, trilobites, and echinoderms. They were nurseries for fish, shelters for invertebrates, hubs of biodiversity. Swimming above such reefs, the seas must have looked alive with color and motion, a true underwater metropolis. But as with every golden age in Earth's history, the Devonian was not immune to catastrophe. Toward its end, a series of extinction events struck, collectively known as the Late Devonian Extinction. The causes are still debated. Some point to climate cooling, others to drops in oxygen levels in the oceans, perhaps triggered by massive plant growth on land altering carbon cycles. Whatever the cause, the effects were profound. Reef systems collapsed, many placoderms, including Dunkleosteus, disappeared, and vast numbers of marine species vanished. It was not as sudden as the asteroid strike that ended the Cretaceous, but it was relentless, unfolding in pulses over millions of years. By the close of the Devonian, the oceans had been reshaped, their rulers humbled, their diversity pruned. And yet, even in loss, new opportunities arose. Sharks, adaptable and efficient, began to spread further. Ray-fin fishes survived and prepared to radiate into the millions of species we know today. The lobefins that endured would carry their legacy onto land, where forests were already spreading, and amphibians would soon crawl. The Devonian was an age of abundance, but also of transition, setting the stage for new kinds of worlds, both in the water and beyond it. Picture yourself floating above a Devonian reef. Below you, armored placoderms move like tanks, their jaws snapping. Smaller fishes dart between coral structures, their fins flashing in the light. In the distance, the shadow of Dunkleosteus passes, a reminder of the power of predators. Near the shallows, a lobe-finned fish pushes itself up, its body awkward but determined, its fins pressing against mud. You watch as it lifts its head, tasting air for the first time. It does not know it, but it is a pioneer, beginning a journey that will lead to frogs, reptiles, birds, and eventually humans. This is the legacy of the Devonian, oceans filled with fish, and the first steps toward a new world waiting above the tide. The end of the Devonian had shaken the oceans. Armored giants like Dunkleosteus were gone, reefs had collapsed, and ecosystems were stripped back. Yet life did not surrender. As the Carboniferous period began, the seas filled once more with communities that looked unlike anything that had swum before. If the Devonian was the age of fishes, then the Carboniferous seas could be thought of as the age of abundance. Crowded, diverse, and often strange, the seafloor was no longer bare rock and rubble. Instead, it transformed into something that resembled a forest. Crinoids, often called sea lilies, anchored themselves to the bottom by long stalks. From their bases rose delicate crowns of feathery arms that stretched into the currents. They fed not by chasing prey, but by waiting, filtering tiny particles drifting in the water. Seen together, entire meadows of them waved in rhythm with the sea, swaying gently like fields of grass. To a slow-moving swimmer, the scene would feel almost otherworldly. A garden with no soil, a forest that bloomed underwater. Among them lay brachiopods. They looked like clams to the casual eye, but they were something else entirely, opening and closing their shells in steady pulses. They crowded the sea floor in huge numbers, carpeting rocks and reefs, filtering the water with quiet persistence. Around them, corals and bryozoans formed small reef-like structures, weaving together habitats for countless other species. In the open water above, ammonites drifted, carried by the currents. Their coiled shells spiraled in endless variation, tight curls, broad whorls, ribbed patterns, and inside each shell, tentacles reached out, steering the animal forward. They were hunters of small prey, but they were also prey themselves, a constant presence that tied the entire food web together. It was in this abundance that sharks found new opportunities. Having survived earlier extinctions, they now flourished, diversifying into forms both sleek and bizarre. Some began to resemble the streamlined hunters we know today, but others became experiments in body design that push the imagination even now. One such form was Stethecanthus. Its most striking feature was the anvil fin that rose from its back, a broad, flat surface covered with tiny spines. What purpose it served is still debated. Perhaps it was a display, a way to attract mates or warn rivals. Perhaps it functioned as a stabilizer in the water. Whatever its use, it gave the animal a silhouette unlike any shark since. Picture a body gliding smoothly through the currents, with what looks like a small ironing board rising from its back. Odd to us, but for millions of years, it worked well enough for Stethecanthus to thrive. Then there were the xenocanths, sharks built for freshwater rivers and swamps rather than open seas. Their bodies were long and eel-like, with a distinctive spine at the back of the head. Some may have used it for defense, others for display. Unlike the short lives of most modern sharks, xenocanths may have lived decades, even close to a century. They remind us that not all sharks were ocean wanderers. Many carved out lives in the rivers that cut through Carboniferous forests, feeding on amphibians and fish alike. But perhaps the most famous of these odd sharks was Helicoprion. Its fossils puzzled scientists for generations. The animal left behind little more than a spiral of teeth, coiled like a buzzsaw blade. Where did it belong? Early reconstructions placed it on the nose, others along the back, even protruding from the body like a strange ornament. Only later did evidence confirm the spiral belonged in the lower jaw. New teeth pushed older ones inward, building the coil. When the animal snapped its mouth shut, that spiral rotated through prey like a circular saw, slicing soft-bodied animals with brutal efficiency. It was a design that feels almost absurd, and yet it endured for millions of years, proof that nature experiments in ways beyond our imagination. While the oceans flourished, the land above was going through its own transformation, one that would shape marine life in subtle but powerful ways. Vast swamps stretched across continents, filled with towering trees and dense undergrowth. These forests were unlike the ones we know today, dominated by giant horsetails, ferns, and club mosses that grew to heights rivaling modern buildings. Insects flourished in this oxygen-rich air, growing to enormous sizes. Dragonflies, with wingspans the length of a hawk, glided between the trees. Millipedes as long as crocodiles crawled across the forest floor. The plants drew huge amounts of carbon dioxide from the atmosphere and released oxygen in return. Oxygen levels soared to over 30%, far above today's 21%. While this was a gift to land life, it also influenced the oceans. With carbon pulled from the air, global cooling events were triggered, glaciers expanded, and sea levels shifted. Nutrients washed into rivers and changing oxygen balances in shallow waters. The land and the ocean were no longer separate worlds. They were deeply linked, each influencing the other's fate. Back in the seas, reefs spread and evolved. Sponges and algae built frameworks alongside corals, creating structures that stretched for kilometers. These were not always the reefs we would recognize today, but they served the same purpose: homes for countless species, cradles of biodiversity, and defenses against the restless waves. Fish darted among them, small ray-finned species beginning to find their niches, while larger predators prowled the open water. Trilobites still crawled across the seafloor, though their numbers were dwindling compared to their Cambrian glory days. The Carboniferous seas were busy, alive with forms that were both familiar and alien. It was an age where ecosystems seemed strong and balanced, with predators and prey woven into stable networks. But time was moving forward, and the conditions that supported this balance were fragile. The slow drift of continents was pushing toward something larger. Land masses crept closer together, and by the time the Permian began, nearly all of Earth's land would unite into a single giant, Pangaea. That collision of continents and the changes it brought to the oceans would begin to reshape everything. The end of the Permian had left the oceans emptied in a way they had never been before. Entire lineages were erased, reefs crumbled into rubble, and nearly all forms of marine life vanished in what became known as the Great Dying. For millions of years, the seas carried a hush, as though the world itself were holding its breath. The once intricate web of creatures that had filled the water was gone, leaving only scattered survivors clinging to existence. It was a time of stillness, but not of finality, because life has a way of rising again from even the most fragile remains. In the earliest Triassic seas, that resilience was subtle. The waters were quiet, and ecosystems were reduced to a handful of species. The complexity that had once defined ocean life had been stripped away, replaced by simplified communities where a few hardy creatures dominated. But slowly, change began. At first, the signs were modest: small shells scattered across shallow seabeds, a few colonies of coral-like organisms, and scattered populations of fishes. Then, one lineage in particular began to surge forward: the ammonites. These spiral-shelled cephalopods had nearly disappeared in the extinction, yet their ability to adapt proved extraordinary. Within a few million years they multiplied again, filling the oceans with their coiled shells. Some were tightly wound, others spread their coils loosely. Some were smooth, while others grew ridges and spines. Their diversity exploded, making them one of the clearest symbols of recovery. They became so widespread and changed so quickly that scientists today can use them to tell the age of ancient rocks. But in their own time, they were not markers but survivors, weaving themselves back into the ocean's food chains and restoring the flow of energy through waters that had nearly gone silent. Their success opened the door for something even more dramatic. The collapse of older ecosystems had left vacant niches, roles in the ocean with no creatures to fill them. It was in this emptiness that reptiles made their move. Descendants of land dwellers, some with bodies shaped for walking, began slipping into shallow seas. Evolution reshaped them quickly, sculpting forms designed for swimming, hunting, and ruling the water. Within a few million years, the oceans were home to animals the likes of which the world had never seen. Foremost among them were the ichthyosaurs, whose name means fish lizards. At their origin, they may have looked awkward, like reptiles not yet fully committed to water, with flexible bodies and limbs that were neither true legs nor true flippers. But soon they transformed into streamlined predators whose shapes rival those of modern dolphins. Their bodies grew sleek, torpedo-shaped and fast, with tails built for powerful propulsion and fins for balance. Their jaws lengthened into narrow snouts lined with sharp teeth, ideal for snapping fish or squid. And their eyes grew enormous, some of the largest of any animal known, allowing them to see in dark or murky waters. Some ichthyosaurs remained modest in size, a few meters long, while others expanded into giants, longer than buses, dominating open seas as apex predators. They were not simply survivors, they were innovators, and they became the first great reptilian rulers of the oceans. Alongside them came another group, very different in design but no less remarkable, the plesiosaurs. Their story began with smaller coastal hunters, called nodosaurs, reptiles that paddled through shallow lagoons searching for prey. From these forms evolved true plesiosaurs, whose bodies were broad and barrel-shaped, driven by four powerful flippers. Unlike fish or ichthyosaurs that swam with side-to-side motions, plesiosaurs used their flippers in synchronous strokes, almost like wings beating through water. It gave them a style of movement unlike anything before, one that allowed both agility and endurance. Early plesiosaurs kept their necks relatively short, but evolution soon stretched them into lengths that seem improbable. Dozens of vertebrae strung together, producing necks several meters long tipped with small heads. They could cruise calmly while their necks arced forward, darting into schools of fish with sudden strikes. The oceans, once quiet after devastation, now hosted swimmers that seemed drawn from dreams. Long-necked, wing-flippered reptiles gliding with calm certainty through recovering seas. The Triassic was not content with only these. It was an age of experimentation, a laboratory of possibilities. Some reptiles became placodontts, stocky animals with crushing teeth suited for cracking shells, some even wearing armor plates across their backs that made them resemble swimming turtles. Others evolved into thalatosaurs, slender-bodied creatures with long tails that slid easily through shallow water. Each of these filled niches left empty by extinction, and each represented nature's relentless creativity. Even crocodile relatives began their first steps into the ocean. Though true marine crocodiles would appear later, the Triassic hosted their precursors, reptiles that lingered in lagoons and river mouths, bridging the worlds of land and sea. While these reptiles explored their futures, the background of the ocean was quietly rebuilding too. Reefs, which had collapsed entirely during the Great Dying, began to form again. Corals were part of this return, though often different types than the ones that dominate today. Sponges and algae also contributed, weaving together structures that sheltered small fish, crustaceans, and mollusks. Bivalves spread across seabeds, anchoring themselves to rocks or burrowing into the sand. Ray-finned fishes, still modest in diversity compared to what they would later become, began expanding steadily, darting in schools through the shallows. And always, the ammonites spiraled upward in abundance. Their shells glittered in the sunlit waters and served as both hunters and prey. But recovery was not a smooth climb. The Triassic carried its own stumbles, periods when climate shifts or changes in sea level interrupted progress. Some reef systems collapsed again, only to be rebuilt later. Some reptile lineages thrived briefly, then vanished entirely, leaving no descendants. It was a reminder that recovery after catastrophe is never straightforward, but messy, full of stops and starts. And yet through all these fluctuations, the overall direction was clear. The oceans were regaining their vibrancy, filling once more with diversity and complexity. If you could drift through a Triassic sea, the scene would feel alive yet still experimental. Schools of small fish shimmer in the sunlight. Ammonites coil and uncoil as they glide in every direction, their shells reflecting faint glints. Near the seafloor, placodont's graze on shellfish, their blunt teeth cracking through hard shells. In the distance, an ichthyosaur darts past, swift and purposeful, a shadow that sends smaller animals scattering, and not far off, a plesiosaur cruises, its long neck weaving lazily from side to side as its flippers beat in steady rhythm. It is not the same ocean that had existed before the Permian extinction, but it is no longer the barren silence that followed. It is something new, a place where old roles have been filled by new actors, where survival has given way to creativity. By the end of the Triassic, this rebuilding had succeeded. The oceans were once again rich and dynamic. Ichthyosaurs held dominion over open waters, plesiosaurs patrolled coastal seas, and early crocodilian relatives prowled lagoons. Ammonites had not only survived but flourished, their endless variations spinning through the currents. Corals, sponges, and algae had raised reefs from rubble, while small fishes wove themselves into every corner of the food web. The oceans had been transformed, not restored to what they once were, but remade into something different. The absence of trilobites and the decline of brachiopods marked the close of an older era, while the dominance of reptiles announced the dawn of a new one. What the Permian extinction had nearly erased, the Triassic had rewritten. From devastation came renewal, and from silence, a new chorus of life. The seas were ready now for what would follow, prepared for even greater experiments, and for the rise of giants that would carry their grace and power into the age of the Jurassic. When the Triassic came to a close, the oceans had already transformed from silence into renewal, but the Triassic carried this recovery into something far grander. The seas of this age were not merely alive again, they were flourishing in a way that revealed the full creativity of evolution. Warmth spread across the globe. Shallow seas lapped against broad continental shelves, and with these conditions came a surge of biodiversity that turned the oceans into bustling kingdoms of motion and grace. Here, reptiles reached extraordinary designs. Ammonites filled the waters with spirals upon spirals, and new dramas unfolded in ecosystems richer than they had been for millions of years. The ichthyosaurs, those swift reptiles that had risen in the Triassic, now grew into giants. In the Jurassic, their bodies became perfected for open water hunting, streamlined in ways that rivaled modern whales and dolphins. Some species reached lengths of 20 meters, enormous predators that prowled the seas with confidence. Their massive eyes, larger in proportion than any seen before or since, gave them the ability to pierce the dim twilight of deeper waters, hunting where sunlight barely reached. Imagine their presence, vast shadows cutting through blue depths, long jaws studded with sharp teeth, sleek forms moving with a speed that belied their size. They were the undisputed rulers of the open ocean, perfectly adapted to chase down schools of fish or ambush softer-bodied prey like squid. Fossils of ichthyosaurs have even been found with unborn young still inside, preserved in stone as a reminder that these great predators gave live birth in the water, their entire lives bound to the sea. While ichthyosaurs claimed the open ocean, another group of reptiles rose to prominence in the coastal shallows and continental shelves. If ichthyosaurs represented power and speed, plesiosaurs embodied strangeness and elegance. Their bodies were wide and muscular, propelled by 4 strong flippers that beat in synchronized motions, allowing them to fly underwater with a grace unlike any other reptile. Some carried relatively short necks and large heads, ideal for tackling sizable prey in sudden strikes, but others evolved necks so elongated that they seem almost impossible, dozens of vertebrae stretching several meters, topped with small, narrow heads that could weave through schools of fish with delicate precision. These long-necked plesiosaurs are among the most iconic images of Jurassic seas, their outlines inspiring myths of sea serpents and lake monsters even in human times. In truth, they were hunters, perfectly adapted to their world, scanning the waters with keen senses, steering with remarkable agility, and feeding in ways that no other reptile could match. Together, ichthyosaurs and plesiosaurs created a layered ecosystem of predators. The giants patrolled the open seas, while more maneuverable forms hunted in coastal waters and reefs. They were joined by other marine reptiles as well. Plesiosaurs, relatives of plesiosaurs with shorter necks and massive jaws, grew into apex predators of terrifying proportions. Some species stretched more than 10 meters long and carried skulls as large as cars, armed with teeth that could crush bone with ease. In the Jurassic oceans, there was no shortage of hunters, each filling a role, each shaped by millions of years of competition and adaptation. Beneath these rulers, the seas were filled with a richness that gave them sustenance. Ammonites, ever the survivors, were now more abundant than ever. Their shells spiraled in endless variety, some tightly coiled, others flaring outward with elaborate ribs and spines. They filled the midwater in dazzling numbers, providing both beauty and food, their presence so prolific that they became one of the defining symbols of Jurassic seas. Swimming alongside them were the belemnites, close relatives of squid, whose bullet-shaped shells left behind fossils that now litter ancient rocks. Unlike ammonites, which carried coiled external shells, belemnites were sleeker, their shells internal, making them closer to modern squid in form. Together, ammonites and belemnites created a ceaseless supply of prey, their swirls and darts across the water forming the base of food chains that stretched upward to the greatest reptiles. Part of what allowed such abundance was the shape of the planet itself. During the Jurassic, the continents were still gathered, but had begun to pull apart, forming new coastlines and shallow seas. These shallow waters are the most productive ecosystems on Earth, where sunlight penetrates deeply and nutrients circulate freely. Reefs thrived in these regions, rebuilt by corals after their long absence during the Permian extinction. They stretched in intricate structures, hosting fish, crustaceans, mollusks, and countless other small creatures. Warmth from a greenhouse climate fueled productivity, ensuring that life had not only survived but was now flourishing with intensity. The Jurassic seas became cradles of biodiversity, bustling with activity from the smallest plankton to the largest predator. To this world, experimentation was everywhere. Ammonites twisted their shells into eccentric shapes, spined, ridged, even oddly coiled forms that seem almost decorative. Plesiosaurs tested different neck lengths, some stretching further with each generation, others shortening back to powerful jaws. Ichthyosaurs reached their peak diversity, some evolving into giants of open water, others becoming smaller, fast-moving specialists. Even fish were diversifying, ray-fin species multiplying into countless lineages that would one day dominate the oceans entirely. Everywhere, the ocean seemed restless, as if still remembering the silence of the great dying and ensuring it would never again be so empty. One of the most striking aspects of the Jurassic seas is how familiar they feel, and yet how alien. To swim through them in your imagination is to recognize the outlines of ecosystems we know today. Schools of fish, reefs buzzing with life, predators patrolling above. But the creatures themselves are different. Reptilian rulers that no longer exist, ammonites in numbers we can scarcely imagine, belemnites darting where squid and cuttlefish now swim. It is a reminder that life creates similar patterns across time, but always with new actors on the stage. The fossils left behind tell us much about this world. Some ammonite beds contain thousands of shells pressed together, silent cemeteries of once living swarms. Complete skeletons of ichthyosaurs show them preserved in death, as if still in motion, with even traces of skin and stomach contents revealing what they last ate. Plesiosaurs lie with their necks gracefully curved, their long spines testifying to the improbable design that carried them through the seas. Each fossil is a snapshot of a world that no longer exists, and together they paint a portrait of oceans overflowing with activity, beauty, and danger. As the Jurassic wore on, these oceans remained stable and rich, supporting their reptilian monarchs for tens of millions of years. But nothing on Earth lasts forever. Toward the end of the period, the climate shifted again, seas receded in places, and ecosystems adjusted. The ichthyosaurs, once so dominant, began a slow decline, though they would persist for many millions more years. New predators waited on the horizon, and new changes in the Earth's surface were already reshaping the planet. For now, though, the Jurassic seas stand in memory as one of the grandest ages of marine life, a time when reptiles flew through water, when ammonites spun endless patterns in their shells, and when warm, shallow seas turned the planet into a cradle of abundance. These were truly oceans of grace, where power and elegance met in forms that seem almost too strange to be real, and yet they were real, enduring for millions of years before giving way to the next chapter of Earth's restless story. The seas of the Cretaceous were different from any that had come before. By now, the Earth had settled into a greenhouse climate, warmer than it had been for tens of millions of years. Sea levels rose high, flooding continents and creating vast shallow seas that stretched across entire regions. These inland waters connected to the open oceans, blurring the line between land and sea and providing endless new habitats for life to explore. In this world, marine reptiles reached their final spectacular act. Ammonites thrived in dazzling variety, and reefs flourished once again with a brilliance not seen since ancient times. At the heart of this story were the mosasaurs. Descended from land-dwelling lizards, these reptiles had returned to the sea and risen to its highest throne. At first they were modest in size, but in the Cretaceous they grew into monsters. Some stretched more than 15 meters, with skulls lined with sharp conical teeth designed for seizing and tearing prey. Their bodies were long and muscular, propelled by powerful tails and flippers that steered them through the water with surprising agility. They were not built for delicate maneuvers, but for dominance, overwhelming their prey with power and speed. Fossil evidence shows that they hunted almost everything: fish, ammonites, turtles, even other marine reptiles. They were the undisputed apex predators of their time, the true rulers of the Cretaceous oceans. To imagine a mosasaur is to picture a body shaped like a giant monitor lizard, stretched and streamlined for the sea. Its jaws could gape wide, swallowing large prey whole. Some species may have lurked in shallow waters to ambush, while others roamed the open seas as relentless hunters. Marks on fossils reveal the violence of their world: bite traces on turtle shells, shattered ammonite shells, even evidence of mosasaurs fighting one another, their teeth leaving scars on the bones of rivals. They were not creatures of quiet grace like ichthyosaurs, nor strange experiments like plesiosaurs. They were raw power, a lineage that rose quickly and claimed the seas with ferocity. The Cretaceous oceans did not belong to mosasaurs alone. They shared their realm with giant sea turtles, some reaching lengths of 4 meters or more, their shells vast shields that carried them across the globe. These turtles swam with steady endurance, feeding on sea plants, jellyfish, and smaller creatures, their lives stretching across decades. Alongside them were marine crocodiles, relatives of today's species but adapted to saltwater. Some, like Dirosaurus, were long-bodied swimmers that prowled coasts and estuaries, while others grew massive, with jaws wide enough to tackle large prey. Together, turtles and crocodiles added weight and diversity to the reptilian cast of the Cretaceous seas. Ammonites and their close relatives, the belemnites, still filled the midwaters in vast numbers, their shells coiled into countless variations. adorned with ridges, spines, and patterns that seem almost artistic. In some regions, entire layers of rock today are built from their remains, silent cemeteries of creatures that once drifted by the millions. They were not passive victims of the age. They hunted actively, using tentacles to capture small fish and plankton, feeding the larger predators above them. Their abundance kept the food chains running, just as they had done for hundreds of millions of years. And below, the seafloor was alive again with coral reefs. After the long absence and instability of earlier times, corals had returned to dominance, building reefs that stretched for kilometers, their frameworks supporting ecosystems of astonishing complexity. Within their branches darted small fishes, crustaceans, and mollusks, while predators circled outside. Reefs provided nurseries for young fish, defenses against waves, and a stage for interactions that had been absent during the leaner times of Earth's past. They were bright, colorful worlds in the warm, shallow seas, buzzing with energy and life. The shape of the planet itself helped create this abundance. During the Cretaceous, continents were breaking apart, forming wide coastlines and shallow inland seas. North America, for example, was split in two by the Western Interior Seaway, a vast body of water that stretched from the Arctic to the Gulf of Mexico. It was filled with mosasaurs, turtles, sharks, and ammonites, a sea that cut across a continent and carried with it all the drama of ocean life. Similar seaways spread across other continents, each becoming laboratories for evolution, where species adapted to unique conditions and predators found endless hunting grounds. It was in these seas that sharks continued their own rise. Though overshadowed by reptiles in sheer size, they remained efficient hunters, diversifying into new forms and filling niches left open by others. Rays also began to appear, gliding gracefully across the seafloor in search of prey. Fishes expanded as well, ray-finned lineages multiplying into countless species. They swam in schools, darted through reefs, or prowled in deeper waters. While reptiles dominated the headlines of the age, the future clearly belonged to fish, which would carry their success into the Cenozoic after the reptiles were gone. The Cretaceous seas were not gentle. They were arenas of constant struggle where survival demanded speed, strength, or strategy. A school of ammonites drifting through clear water might suddenly scatter as a mosasaur lunged from below, jaws gaping, tail thrashing in pursuit. A giant turtle might graze calmly on sea plants, only to find itself harried by a crocodile lurking near the shore. Belemnites shot jets of water to escape predators, leaving behind trails of ink in desperate defense. Life thrived, but it did so in the shadow of constant danger. Yet for all their danger, the Cretaceous oceans were also beautiful. Reefs glowed with color, fish schools shimmered in patterns, ammonite shells gleamed with ridges and spirals, and the vast bodies of marine reptiles moved with a kind of raw majesty. They were seas at their most spectacular, filled with creatures that seem almost mythical to us now. But this age, like all others, was finite. Near its end, the Cretaceous world trembled with changes. Volcanic activity altered climates, sea levels shifted, and ecosystems felt new pressures. And then came the event that would change everything. The asteroid impact that marked the boundary between the Cretaceous and the Paleogene. In an instant, the mosasaurs, the ammonites, and countless other marine creatures disappeared. The apex hunters of the deep were gone. They left the oceans to yet another wave of survivors who would rebuild once again. The Cretaceous oceans remind us of the fleeting nature of dominance. For a brief span of millions of years, mosasaurs ruled with unmatched power, ammonites swirled in endless abundance, reefs blossomed, and turtles and crocodiles grew to immense size. It was an age of spectacle, of oceans at their most dramatic, where predators reached their final peaks before vanishing into extinction. What remains are fossils, bones turned to stone, shells pressed into rock, echoes of a world that once teemed with grace and danger. And as we follow their story, we see not only the loss of these giants, but also the resilience of the seas, always ready to create again after destruction. The curtain was falling on the reptiles' reign, but the oceans were not empty for long. When the age of reptiles came to its abrupt and violent close, the oceans changed once again. The great marine reptiles of the Cretaceous vanished in the shadow of an asteroid's impact, leaving empty waters where mosasaurs, plesiosaurs, and ammonites had once thrived. For a time, sharks and fishes held the advantage, filling niches left behind by the fallen giants. But evolution never leaves a space unfilled for long. In the millions of years that followed, the oceans welcomed new rulers. Not reptiles this time, but mammals, creatures whose ancestors had walked on land and breathed air beneath open skies. Their return to the sea marked one of the most extraordinary transformations in the history of life. The story begins on land, with small, hoofed mammals that roamed coastlines during the early Paleogene. Some ventured into shallow water to feed, wading like today's deer or tapirs. Over countless generations, certain lineages became more and more adapted to aquatic life. Their legs shortened, their bodies stretched, and their nostrils shifted higher on the skull. Fossils from species like Pacetus and Ambulocetus show this transition in progress. Pacetus still resembled a land mammal, slender and four-legged, but its ear bones reveal adaptations for underwater hearing. Ambulocetus, sometimes called the walking whale, could move clumsily on land, but swam with powerful strokes in rivers and lagoons, its body part mammal, part early aquatic predator. These creatures stand as remarkable snapshots of evolution in motion, showing step by step how a terrestrial lineage surrendered to the sea. As time went on, these proto-whales became more specialized. Their hind limbs shrank, eventually disappearing into the body. Their tails grew stronger, developing flukes that could drive them forward with powerful motions. Their nostrils slid further back along the skull, becoming blowholes, allowing them to breathe while remaining mostly submerged. By the late Eocene, about 40 million years ago, fully aquatic whales had emerged. Some were slender and swift, hunting fish with sharp teeth, while others grew massive, experimenting with the bulk and size that would later define the great whales. From shoreline mammals only a few meters long, whales had become masters of the open ocean. The earliest whales were predators, often with sharp teeth and jaws designed for seizing fish or squid. They hunted like crocodiles or large seals, ambushing prey and swallowing them whole. But evolution continued to shape them, and eventually two great lineages diverged. One became the toothed whales, ancestors of today's dolphins, orcas, and sperm whales. The other became the baleen whales, which abandoned teeth altogether in favor of keratin plates that allowed them to filter vast clouds of plankton and small fish. This shift was revolutionary. Instead of chasing prey one by one, baleen whales could open their immense mouths and swallow hundreds of liters of water, straining food through their baleen-like sieves. It allowed them to grow to sizes unmatched by any creature before or since. The largest animals ever to live on Earth are not dinosaurs or reptiles, but whales, whose bodies can stretch more than 30 meters and weigh as much as dozens of elephants combined. The oceans of the Neogene, tens of millions of years after the dinosaurs vanished, became their stage. Baleen whales cruised slowly across great distances, following the seasons and the blooms of plankton that fed them. Toothed whales became social hunters, developing echolocation, a biological sonar that allowed them to see with sound in dark waters. Schools of dolphins chased fish with coordinated speed, while sperm whales dived into the black depths, hunting giant squid in battles that remain largely hidden from human eyes. It was a new kind of dominance, built not on reptiles with teeth and scales, but on mammals with intelligence, endurance, and a mastery of the ocean's rhythms. But the whales were not alone in these seas. Sharks, ancient survivors that had endured every extinction, found themselves with new opportunities. Some lineages grew immense, larger than anything before or since. Chief among them was Carcharocles megalodon, the largest shark to ever live. Estimates suggest it reached lengths of 15 to 18 meters, with jaws that could open wide enough to swallow a human whole with room to spare. Its teeth, triangular and serrated, were as large as human hands, designed to slice through flesh and bone with terrifying efficiency. Fossil teeth are found around the world, sometimes in abundance, reminders that these giants swam in almost every ocean. Megalodon was more than just large. It was a true apex predator. Evidence suggests it hunted whales, biting into their flippers to disable them before delivering fatal blows. Fossil whale bones have been discovered with deep gouges matching the size and shape of Megalodon's teeth. They are silent testaments to encounters where the hunter triumphed. It must have ruled the seas with a presence unmatched, its shadow enough to scatter schools of fish and make even other predators give way. In the food chains of the Miocene and Pliocene oceans, Megalodon stood at the very top, yet even giants can fall. Around 3 million years ago, Megalodon disappeared. Its extinction remains one of the great mysteries of marine history. Several factors likely combined to seal its fate. Climate cooled, shrinking the warm water habitats where it thrived. Sea levels shifted, altering coastlines and reducing the shallow nurseries where its young could grow safely. And perhaps most importantly, its prey changed. Many of the smaller whales it hunted declined, while larger baleen whales spread. These whales migrated into colder waters where Megalodon could not easily follow. Competition with other predators, such as orcas, may have added further pressure. Whatever the precise causes, the result was the same. The greatest shark the world had ever seen faded into extinction, leaving behind only teeth as evidence of its once dominant reign. While Megalodon vanished, whales endured and diversified further. The modern forms we know today, blue whales, humpbacks, orcas, dolphins, arose during these later chapters of the Neogene. They inherited seas shaped by millions of years of trial, evolution, and extinction, and they became the giants and hunters of the modern age. The oceans themselves began to resemble the world we know, with continents close to their present positions, currents circulating in familiar patterns, and ecosystems taking on modern forms. Coral reefs flourished again in tropical waters. Kelp forests spread in cooler seas, and coastlines became hubs of diversity. The rise of mammals in the oceans is a story not only of biology, but of resilience. After reptiles fell, it might have seemed as if the oceans would never again see rulers of such scale and power. Yet within a few million years, mammals had stepped into the role, adapting in ways that astonish us even now. From deer-like ancestors walking on muddy riverbanks came blue whales, longer than any dinosaur. From small predators in shallow seas came dolphins, with sonar precise enough to track fish in darkness. From humble beginnings, they built a new age of ocean dominance. And even as the giants of the sea shifted, the oceans themselves remained the stage where life constantly renews itself. Each extinction cleared the board, and each recovery filled it again, with players stranger, larger, or more ingenious than those before. The Cenozoic seas, shaped by mammals and sharks, remind us of that cycle. They were not static, but alive with change, and their stories carry forward into the oceans that surround us today. Across billions of years, oceans have given rise to endless experiments, whole dynasties of creatures that appeared, flourished, and then disappeared forever. Yet not everything has been lost. Scattered through the seas are species that feel like time travelers, living forms whose ancestors swam alongside trilobites, ammonites, or even the first fishes. They are sometimes called living fossils, though of course they are not frozen relics but survivors, still evolving in their own ways, still alive today. Meeting them is like glimpsing fragments of worlds long gone, pieces of deep history that managed to hold on against the odds. One of the most famous of these survivors is the coelacanth. For decades it was known only from fossils, its story seemingly finished 65 million years ago. Then, in 1938, a fisherman off the coast of South Africa pulled up a strange blue-scaled fish with lobed fins and an unmistakable outline. It was a coelacanth, alive and breathing in the 20th century, a creature thought to have been extinct since the time of dinosaurs. Its discovery stunned science. Here was an animal that had watched the rise of reptiles, survived the asteroid that ended them, and persisted in hidden corners of the ocean for millions of years. Coelacanths are unlike modern fish in many ways. Their fins are lobe-like, supported by thick bones that resemble the limb bones of early tetrapods, the same lineage that gave rise to land animals. Their bodies move with an undulating rhythm, their paired fins rotating almost like the legs of a slow-moving animal. They are not the ancestors of living land creatures, but they are close relatives of that ancient branch, and in their motion one can almost glimpse the evolutionary experiments that shaped the first steps onto land. Today, coelacanths dwell in deep waters along steep volcanic slopes, rarely seen by humans. When lights fall on them, their scales shimmer in hues of deep blue, as if echoing the twilight zones they inhabit. To look into their eyes is to connect with a lineage that stretches back 400 million years. Another emblem of ancient survival is the horseshoe crab. Its body, a hard domed shell with a spiked tail, seems alien to modern eyes, but it has remained nearly unchanged for hundreds of millions of years. Horseshoe crabs scuttled across seafloors long before the first dinosaurs hatched, and yet they still gather in vast numbers along beaches today. Their blue blood, rich in copper rather than iron, clots in the presence of bacterial toxins, and for that reason, it has become invaluable to medicine, used to test the safety of vaccines and drugs. These creatures, which seem so simple and strange, have saved countless human lives without most people ever realizing it. Watching them come ashore to spawn under the moonlight, thousands at a time, is like witnessing a ritual as old as the continents themselves. The Nautilus, too, carries echoes of vanished seas. With its coiled shell and trailing tentacles, it resembles the ammonites that once filled the oceans by the millions. Yet ammonites perished in the Great Extinction at the end of the Cretaceous, while nautiluses endured. Their shells are marvels of design, divided into chambers filled with gas that allow them to rise and sink at will. They drift slowly through deep reefs, scavenging with delicate tentacles, their striped shells spiraling in patterns that seem almost mathematical. For over 500 million years, relatives of the Nautilus have glided through oceans, their shells leaving traces in rocks from every era. To see one today is to glimpse a fragment of that ancient continuum, a delicate survivor of ages when reptiles ruled above and ammonites ruled below. Beyond these familiar survivors lie mysteries still unfolding. The deep sea, which covers the majority of Earth's surface, remains largely unexplored. Within its darkness dwell creatures as strange as any that have ever lived. Among them is the giant squid, long a subject of myth and legend. Sailors once told of krakens capable of dragging ships into the depths, stories that blended fear with imagination. For centuries, no one had seen such creatures alive, only the occasional body washed ashore or torn remains found in the stomachs of sperm whales. But in recent decades, cameras have finally captured them in their natural habitat. Enormous, elusive beings, with eyes as large as dinner plates and tentacles lined with suction cups. They can reach lengths of over 12 meters, moving with an eerie grace in the midnight waters. Yet the giant squid is only one mystery. Its relative, the colossal squid, grows even larger and stranger, with hooks on its tentacles and eyes possibly the largest in the animal kingdom. These creatures live so deep that almost nothing is known of their lives, save for hints left behind in the scars found on sperm whales that hunt them in the blackness. Encounters between whale and squid remain among the most dramatic battles in the natural world, almost never seen but written in the marks on living bodies. Other deep-sea dwellers reveal adaptations that feel more like dreams than biology. The anglerfish, with its glowing lure, drifts in darkness, using its bioluminescent beacon to attract prey. Some species are so small and delicate they look like drifting ornaments. Yet their jaws can open wide enough to engulf prey larger than themselves. In many species, the males are tiny compared to the females, living their entire lives fused to their partners, sharing bloodstreams in a bizarre form of parasitic union. Then there is the gulper eel, whose mouth opens into a cavernous pouch, capable of swallowing fish nearly as large as itself. Its long, whip-like tail often glows with light, trailing behind like a living lantern in the abyss. These creatures are not echoes of ancient seas in the same way as coelacanths or nautiluses, but they remind us that evolution is still experimenting, still crafting forms as strange and wondrous as anything in prehistory. The deep sea, isolated and stable for millions of years, provides the canvas. Life there is shaped by pressures so immense it would crush human bodies, by cold near freezing, and by darkness broken only by the faint glow of living light. It is perhaps the closest thing we have to a modern frontier of discovery, a place where unknown creatures still wait in shadows beyond our reach. Scientists estimate that thousands, perhaps millions of species remain undiscovered in the oceans. Each deep canyon, each unexplored ridge, may harbor life forms that no eye has ever seen. Already, submersibles and cameras have revealed creatures that seem almost fantastical. Gelatinous beings that pulse like alien lanterns, fish with transparent heads revealing their brains, shrimp that snap their claws with such force they create bubbles of heat and light. These discoveries remind us that the oceans are not relics of the past, but living worlds, still filled with secrets and surprises. In this way, the ocean is both a memory and a mystery. It carries survivors from the most ancient chapters of Earth's history, living fossils that bridge across eons. It shelters monsters of the deep that once belonged only to legend, and it hides in its vastness species that may one day astonish us as much as the rediscovery of the coelacanth did nearly a century ago. The oceans hold the past, shape the present, and guard the unknown future, always larger than our imagination, always deeper than our reach. The ocean is both a place and a story, and as we follow its chapters across time, we come to see it as something more than water and waves. It is a kind of memory, holding fragments of everything that ever lived, yet it is also an eraser, washing away traces until only hints remain. To think of the oceans in this way is to stand at the edge of something vast and timeless, a mirror where past and present ripple together. Close your eyes for a moment and let the waves carry you backward, not just years or centuries, but millions upon millions of years, until the world is unrecognizable. Imagine the seas of the Cambrian, alive with creatures whose bodies were experiments in form, eyes peering from stalks, spines and frills jutting from soft bodies, trilobites crawling like armored beetles across the seabed. In those waters, life was still finding its vocabulary, sketching the first rough drafts of what creatures could be. It was chaotic, strange, and utterly new. Drift further into the Ordovician shallows, where reefs began to build their stony frameworks and jawless fishes wriggled through the currents. Giant cephalopods patrolled the depths, their long shells gleaming as they drifted after prey. The ocean at that time was an empire of invertebrates, ruled by forms that would one day vanish but left their mark in stone. The Silurian and Devonian seas brought further transformation. Reefs more intricate, fishes with bony plates and heavy jaws, some destined to crawl onto land and explore the unfamiliar air above. Dunkleosteus, with its armored head and crushing bite, was a predator like no other, and yet even it would pass into memory, leaving behind only fossils and shadows. In the Carboniferous and Permian, oceans blossomed with life, only to be struck down in the Great Dying, when almost everything perished. If you close your eyes and picture those waters, you might sense silence, an emptiness stretching across the sea, but silence never lasts. In time, new creatures swam again, filling the void with ichthyosaurs shaped like torpedoes, plesiosaurs with necks that seemed to defy design, and reefs that pulsed with life once more. The Jurassic seas shimmered with abundance, ammonites swirling in spirals, plesiosaurs striking with massive jaws, ichthyosaurs diving deep with eyes as wide as lanterns. Then came the Cretaceous, with mosasaurs rising to supreme power, enormous turtles drifting like islands, and reefs dazzling with color. Each age wrote its own verse into the ocean's song, each one unique yet bound together by the same water that covered the globe. And then came the mammals. whales that grew larger than anything before, dolphins clicking their way through dark waters, and sharks that reached monstrous scale, megalodon biting into the bones of whales with teeth as long as a man's hand. Even these titans were temporary, fading away as the seas continued to change. Now in the Quaternary, we find seas that feel familiar, where blue whales dive in arcs of power and grace, where orcas hunt in packs with precision, and where coral reefs light up the tropics with color. Yet beneath this familiarity lies the same truth that has always been there. Oceans are not still, they are in motion, changing, reshaping, erasing, and renewing. The survivors remind us of this continuity. A coelacanth drifting in volcanic depths, its lobed fins moving like ancient limbs, is a living bridge to a world 400 million years gone. A horseshoe crab crawling ashore beneath the moon recalls rituals older than any human memory. A nautilus drifting with its perfect spiral shell echoes the ammonites that once filled entire seas. And the deep still hides giants and mysteries. The colossal squid, the anglerfish with its living lantern, the gulper eel with its cavernous mouth. For all we know, there are creatures out there stranger than anything imagined, still unseen, waiting in the darkness. The ocean holds both presence and absence. It remembers in fossils, in shells pressed into stone, in skeletons buried beneath silt. Yet it also forgets, erasing with currents, with tectonic shifts, with the slow grinding of time. Most of what has ever lived is gone without trace, dissolved back into the fabric of the sea. To think of this is to understand that the oceans are not just stages for life, they are editors, deciding what stories survive. And yet, in every wave, in every current, there is continuity. The molecules of water that cradle a blue whale today once touched trilobites, ammonites, ichthyosaurs, and mosasaurs. The sea is a cycle, endlessly reusing, endlessly renewing. To swim in it is to touch deep time itself, to be surrounded by the same medium that shaped all life. Perhaps this is why the ocean feels so mysterious to us, why its depths stir both awe and unease. It is too vast to master, too deep to measure completely, too old to fully comprehend. It carries the ghosts of every era, from the first spark of multicellular life to the giants of today. When we listen to the sea, when we watch its horizon, we are in some way listening to the voice of the planet itself, speaking across billions of years. So let your mind drift one last time, as if carried by a slow current. Picture the seas filled with creatures now gone, ammonites spiraling in clouds of shells, ichthyosaurs slicing through the depths with lantern eyes, mosasaurs surging with power, Dunkleosteus snapping its armored jaws, trilobites swarming across a reef, nautiluses drifting like living fossils among corals. Each scene overlaps the next, a dreamlike panorama of oceans layered upon oceans. The water becomes a mirror, reflecting not only what has lived, but what still lies hidden. The ocean shaped the path of every creature that ever walked, flew, or swam. It shaped us too, for our earliest ancestors came from its shallows, carrying its imprint in our cells. In that sense, the ocean is not only history, but home, the cradle from which all life emerged, and the keeper of stories longer than memory. As we close this journey, there is no need for an ending. The sea has no end. It continues, restless, mysterious, eternal. Its waves will still carry the echoes of ancient worlds long after we are gone. All we can do is listen, imagine, and let it remind us of our place within its story. A story as deep and timeless as the water itself.